Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest's Sciences and Mathematics TV channel. Today we are going to look at a technique in integration, which is basically the rational integration of rational functions. And in our study of numbers, we say that a number that can be expressed in terms of a over b, where b is not equivalent to 0, then therefore this one can be regarded as a rational number. And therefore, we're going to use this specific kind of analogy in trying to solve problems for integrals which are going to assume this specific format. So this one, suppose we have a function qx, which is rational. We can have a relationship whereby we're going to have this function q of x, or qx represented by f of x, as a numerator part of that specific rational function, and the g of x representing rather the denominator and the numerator part of those specific section of the rational function respectively. So suppose we have a qx being a value which is 2 over x squared minus 1. We can be able to find an integral of such a kind of a function by trying to, of course, give partial fractions over this specific function. And in this case, we are talking about the concept of fractions. So therefore, if you try to look at the numerator, rather the numerator for this one, we can see that this is a difference of the squares, whereby we can be able to express this one as x plus 1, and then the next, or rather x minus 1. And then this other one is going to be a minus over 1 over x plus 1 respectively. So if you try to look at this, the multiplication of this is going to give us this, and then the sum of the two on the numerator are going to give the denominator the numerator is going to give us a sum of 2. So therefore this partial can be expressed in terms of partial fraction as such. And if we use this specific strategy for finding an integral, then therefore we're going to have a sum over the integral of these two partial fractions, which are going to be given as such. Sorry for that. So the expression that I've given on my right side, of course, is going to be a partial fraction decomposition of this specific function. And therefore it follows that the integral of this specific function, which is qx dx, can be given in terms of the partial the integrals of these partial functions of this specific expression, thereby implying that the integral of 1 over x minus 1 dx, and then plus, or rather this now is going to be a minus the integral of 1 over x plus 1 dx given as such. So this is going to give us the over of a minus of that specific integral. And from this, of course, we can apply the logarithmic rule for integration of functions, whereby we're going to have this one as the natural log of x minus 1, and then minus the natural log of x plus 1, and then plus c given as such. So therefore, from this one, we can just have a variation of this. For the negative of logarithms, we know that that's a division, and therefore this one can as well be given as the natural log over x minus x minus 1 rather, and then all over the x plus 1, and then we have plus c given as such. So therefore, if you try to find a rational function that has been given as such, we're going to express it in terms of its partial fraction decomposition of this specific function that we have given, and then we can be able to find the overall integral part of this specific function using the logarithmic rule that we've stated in one of our discussions. So therefore this is going to give us the overall answer for this, given as the natural log of x minus 1 minus the natural log of x plus 1 plus c given as such. So we're going to use the same approach if we come across such a kind of functions, so that they're going to assist us know how we can be able to calculate such a kind of integrals. So that is it for now, guys. Catch us in our other video where we're going to have the same. Kindly check in our description boxes for links of various videos which are similar to this, so that they're going to assist us, of course, achieve the same. So that is it for now, guys. Bye. God bless you.